We're going to look at how we can apply differential equations to examples and scenarios containing exponential growth and exponential decay, a topic you may have learned about in Algebra 2 or pre-calculus. Well, exponential growth and exponential decay come from differential equation modeling and is perhaps the most ubiquitous example of how we can apply differential equations to everyday life. For exponential growth and exponential decay appear in mathematical and theoretical biology, they appear in physics, they appear in engineering, and they appear in economics as well. So let's take a look here at exponential growth and exponential decay. So exponential growth and decay, okay? Exponential growth describes a scenario where quantity n has an unlimited amount of resources and thus the quantity is able to grow at an ever-increasing rate without stopping. It grows at an ever-increasing rate because they don't have to worry about running out of resources, so they can continue to consume more resources at an ever faster rate, okay? So exponential growth and exponential decay is recognized by the hallmark sign that the rate of change of the quantity, dn over dt, is proportional to the current quantity at all times. So dn over dt equals k over n. And it actually turns out when you study physics and biology and economics and engineering, this particular equation arises naturally from these studies, and thus exponential growth and exponential decay govern many aspects of modern science and mathematics, okay? So this is the exponential growth differential equation right here. The derivative of n with respect to time t is equal to k times n, where n is our current quantity at that time, okay? K is a constant of proportionality known as the growth/decay constant. It describes the rate at which the quantity increases or decreases. If k is greater than 0, you're going to have an exponential growth, and if k is less than 0, you're going to have an exponential decay. So solving the exponential growth equation, okay? So solving the exponential growth equation is nothing more than an application of separation of variables. So we cross multiply and separate the equation, so we have all n variables on one side and all t variables on the other side. We're going to keep k to the right-hand side. So that means we're going to have dn over n equals k dt. The next thing we're going to do is we're going to find the antiderivatives of both sides, which means the antiderivative of dn over n is going to be a natural logarithm of n, and the antiderivative of k dt is going to be kt plus c. And then we're going to use our initial information to solve for the constant of integration. Okay? So in this case right here, with t equals 0 being the most common type of common condition, because we always start off at 0 of some initial quantity, that means we're going to have k times 0 plus c gives us c. And then on the left-hand side, we're going to have the natural logarithm of our initial quantity and not initial amount of quantity, initial amount slash quantity. So we're going to get c equals the natural logarithm of n naught. And then lastly, right here, okay, we're going to solve the resulting equation for n. So right here, at this point, we have natural logarithm of n equals kt plus the natural logarithm of n naught. So what we're going to do is we're going to apply Euler's number to both sides. We're going to exponentiate both sides, which is going to give us n equals e raised to the kt plus the natural logarithm of n naught, okay? Or applying logarithm rules, e to the kt times e to natural logarithm of n naught. However, since e and natural logarithm are inverse functions, they're going to cancel out, and it's going to leave us with just n naught times e to the kt as our solution, okay? So if you're ever asked to solve this explicitly, this is a problem-solving process you'll carry out, just an application of separation of variables. But if you're not asked to solve for it, say on a multiple choice portion of a test, okay, what you can do is if you recognize the exponential growth or decay differential equation, you can immediately write down the solution as n equals n naught ek of t. Or if it's y equals y naught ek of t. And that will give you your immediate solution. So applying exponential growth, okay? Oftentimes you'll be looking at exponential growth problems to solve, okay? So meaning not looking at how to solve the differential equation, but taking the solution differential equation that we just found and using that to model real-world scenarios. So in that case right here, the idea, there's a clear-cut process you can use to solve these things I've noticed, okay? So what I like to do is first write your exponential growth equation with initial condition n naught. Okay? The next thing you're going to have to do is determine what your growth constant k is. Okay? So that's where you're going to use a second data point, which is usually some later time t1 and some later quantity n1, to solve for and determine what your growth constant is, okay? Or decay constant, okay? So then what you're going to do is in step 3, you're going to solve for the quantity at time equals c, or when the quantity reaches a level n naught, okay? So typically they'll ask you for what the quantity is at some specific time, or they'll ask you for what the quantity, for the time when the quantity reaches a certain specific level, okay? So one or the other, time at t equals c, or the time when the quantity reaches a specific level, vice versa, okay? So let's see what this looks like in practice, this applying exponential growth process right here. So a colony of bacteria is known to grow at a rate that is proportional to the current population of bacteria present, okay? The bacteria start with an initial population of 30 cells and has a population of 250 after 2 hours. At what time t, where t is measured in hours, will the population exceed 1250 bacterial cells? Okay, so we can recognize this as an exponential growth situation here because it tells us that the growth occurs at a rate that's proportional to current population of bacteria present. So what we can do here is instead of solving our differential equation, we can immediately jump to the end since we know our solution to the differential equation, and we can write down n of t equals 30 e k of t. Again, n naught is going to be our initial amount, okay? So in this case, if we start with 30 cells, n naught is going to be 30, so we're going to have n of t equals 30 e k of t, okay? So now what we need to do is solve for our growth constant k here. So we plug in t equals 2, and then n of t equals 250. So n of t is our population at 2 hours, which is 250, and we plug in t equals 2. So that's going to give us 250 equals 30 e to 2k, which is going to give us 8.3 equals e to 2k. So we can solve this by taking natural logarithm on both sides to get the natural logarithm of 8 plus 8.3 equals 2k, or k equals natural logarithm of 8.3 divided by 2, which is approximately 1.6. So now in our third step, it asks at what time t, where t is measured in hours, will the population exceed 1250? Okay. So in this case right here, we're going to have 1250 equals 30 e to the 1.06 t. That's our population. And now we have to solve for this time t when this population hits 1250. So we divide both sides by 30, 41.6 is the result, and we get 41.6 equals e to the 1.06 t. So we take the natural logarithm of both sides, okay? And we get natural logarithm 41.6 equals 1.06 t, which gives us t equals natural logarithm of 41.6 divided by 1.06. Or our bacteria is going to reach a population of 1,250 cells at t equals approximately 3.158 hours.